and please bear with me. And I'll share with you the link. Link will start within 2-3 minutes. So you won't be able to access it. You can only log in.
So there is no link yet in the chat.
Here it goes. So I'll allow you to start having the quiz within 2 more minutes. Precisely 3:35 it will start by my watch. You'll have 5 questions, 5 minutes. All of you have got access to the link?
Yes, sir.
Great, great.
Sir, I am not able to see the link, sir.
What option you are using? You are on what laptop?
Yes, sir.
I can't help, because I have shared. You haven't got Tanay. What you have not got? I mean, you have got the link but unable to open. What is your problem?
No, I can't see the link in the chat, sir.
Somebody send him through WhatsApp or anything else. I have again sent you.
Sure, sir. We'll send it to WhatsApp.
So now you guys can access it. I have allowed. So time starts. Last 1 minute left. Five seconds. It's over now. Shall we start?
Yes, sir.
So Tanay, you wrote the test?
Yes, sir.
So we are starting volatility models. We'll have a little more interactive session today. I want you guys to speak up at least. Otherwise, I'll go slow. So most of the time there will be a silence, deafening silence. So what do you understand by volatility? How do you perceive what is volatility? Come on, speak up.
So the fluctuations, spikes in the data.
Anyone else?
The change in one data due to effect of the another data change.
Come again.
Change in one data due to the another data.
Suman Kumar Gupta ji, can you throw more light on this issue?
So like in BSC, like if market goes up, what if our shares price, one company's share price is either going up or down?
Suppose I can just talk about BSC. So what do you say that? I'm not saying that. I'm assuming there's nothing else, only BSC. Then is there no volatility?
There is volatility, sir.
There's volatility. So what is that? The way Tanay said that there might be, what did Tanay said? Yes, Suman Kumar Gupta ji.
Sir, up to my knowledge, volatility is the change.
Volatility in change.
Volatility means the change. That's all I know.
ठीक है. Suman has made good attempts. Let's look forward to some other people.
Okay, thank you.
Tanushri is there? Is she around?
Yes, Akshay is here.
No, I'm asking about Tanushree Todi. Is Tanushree there?
Yes, sir.
Yes, Tanushree. What's your opinion? What's your take on volatility? What is volatility? Tanushree is one of these students who quite often has issues, queries off the line. So I remembered her name. Yes, Tanushree. Please go ahead. What is your take on volatility? When I say volatility, what do I mean? Yeah, please go ahead. Come on.
Hello, sir. Can you hear me?
Yeah, I can hear you. I'm asking, what is your take on volatility? What is volatility?
Yeah, so there's some issue with my internet. So it might be the fluctuation which the share prices faces due to the market conditions.
Suppose I say fluctuation, all three of you are saying one and the same thing. But how to estimate that fluctuation? Simple. Volatility is fluctuation in price. Perfectly. Well taken. Now the next question is how to estimate it. Akshay want to say something. Akshay, please, would you like to chip in?
Yeah, so it would be the variation of a trading or a stock price over the series of time or something.
No, my question is how to estimate the volatility. If it comes to estimating, what is the easiest, simplest way according to you? Up to this point, we'll take it that fluctuation in share price can be termed as volatility for that particular share or index. If it is BSC, we are talking about volatility in BSC. It is Dow Jones Industrial Average, we are talking about Bovespa, we are talking about Bovespa's volatility. But next obvious question is how to estimate it. Enough of talking. Let's say come to the estimation.
So by variance,
Variance. How do we estimate variance? Yes.
So by dividing the mean, that value by the mean of the total set of values.
So somewhere or the other, Amanchita is correct. Some or the other, I mean, the way is that we have got price, then price is usually converted into returns, and from return we have got mean return. Then we looked at all the prices, how they are deviating from mean, and then we square it, add it, and then we take the mean, and under root it becomes standard deviation. And if you don't take under root, it becomes variance. As simple as this. So if you look at the construction of how we have just talked about variance, then variance, or I prefer to call SD because that is the more elementary thing. So SD is, if I say that series return is X R or X, same if we say that TX bar stands for X minus X bar, means deviation of values. So if I use the term R, then mean R, so dr bar. If I just try to give the similar notation, we calculate the deviation, square it, mean it, and we have got under root of it, it becomes standard deviation. So what we are doing, we are practically looking at the dispersion, deviation of a return series or the series with its own mean. So deviation from the mean is practically taken into consideration. All the means have been taken into consideration, squared it so that plus and minus means are, the deviation, plus and minus deviations are taken into account. Absolute deviations have been taken into account. Irrespective of that is minus or plus. So that's why square is done. Then we take the mean of that square of deviation, and then that's. So this is one of the most historical way, whether you call VAR or SD. I prefer to call SD. I show it by sigma usually. So this is the most preferred way to talk about volatility. And when we say volatility, the another name for this, the thing what is being represented by volatility is risk. In a way, when we talk about volatility, we are talking about a risk present in the return series or in a particular stock, which is represented by sigma. If I just try to give you some utility, let's talk about stock market. When we talk about stock market, then stock market, and you want to make portfolio. When you want to make portfolio, then with whatever theory you want to use to make portfolio, Markowitz portfolio theory becomes one of the most popular, acceptable theory. And there also you have to have two main inputs for every stock. You have taken a stock one. So for these stock, you have to have the mean return R1, mean I'm saying, and then standard deviation of 1. And if you have another, if you want to make portfolio, then you have to have R2 and sigma 2. So what is this? This is also the same thing what we have just talked about. And if I understand that in some or the other course, you would have been asked to calculate the standard deviation or variance, whatever it is. So when you want to make portfolio, you have to have input of these things. So it means somewhere or the other, I'm just trying to highlight the utility of sigma or utility of volatility or a measurement of risk. Practically, when we talk about portfolio, then this represents return, whether expectation or historical, and this represents risk, again, present or historical. So portfolio takes into consideration both risk and return, and then a portfolio is made, and then in the portfolio return is estimated and portfolio risk is estimated using Markowitz portfolio theory. There are other, but this is one of the most elementary. Practically, whatever form of portfolio you are building, you have to take into consideration the risk and return which are possible in the individual assets or securities or stocks. That depends what type of portfolio you are interested in. If I give you another utility, I'm intentionally highlighting the utility. You by now, I believe that most of you have got the exposure to derivatives market. And in derivatives market, I believe strong conviction that you should have understood about futures and options. If you have not, then your GK is poor. Nobody teaches these things. These are general knowledge. So futures and options. So when we talk about futures and options, then what happened? Especially if I talk about futures, when you deal in futures, you don't pay anything. Nothing is paid. You'll be surprised to know. Can somebody throw some light on that when I say nothing is paid when people buy or sell futures? Anyone? Any idea? You are 6 months old here in this IBM Pune and finance team. This is part of GK now. Come on. React. Come on, react. When I say that nobody pays anything to anyone, yeah.
Sir, it's just a contract between two parties on the underlying.
So when we buy or sell, you take a long or short, whatever position on futures. Do you pay something? The question was this payment part.
On
I'm not
exchanges,
asking about
we
futures.
need to pay
I'm assuming
margin.
that you know futures and options. You should know. If you don't know, learn it. Yeah. So I'm talking about question is, does anyone pay anything to anyone?
Sir, we pay margin to the exchange.
Here, how do you pronounce your name? Punajit.
Punajit.
Punajit. Sorry. Is correct. You pay attention to what he said. He said nobody pays anything to anyone. Rather, something known as margin is paid. Margin is nothing but security money. Please understand. When you want to buy a land and you want to block the deal, then you probably give some advance. That is some security. Margin is also security money. So my point remains there. Then nobody pays anything to anyone. Security money is paid so that you do not ditch later on if you are going to have losses in the contract. My question is, who decides? Punaji probably again would like to chip in. Who decides how much money to be paid as margins?
So based on the span margin that NSE has.
How does span margin is estimated?
So that's a very complicated process.
Complicated process. When we say span, the margin is again based upon, something known as VAR. I have discussed this VAR in context when I was teaching VAR. This you remember, vector autoregressive model. And I said this is value at risk. So value at risk is also estimated with the help of sigma. Are you with me?
Yes, sir.
So the point here I'm trying to highlight is the margin is based upon risk. Higher the risk, higher the margin. Pretty obvious. That is estimated with the help of, again, whatever mechanism they have, that's based upon VAR. And VAR is nothing but one of the easiest ways. There are many ways, again. If you check with my research Google Scholar page, you'll find that I've written very nice paper on VAR. So there I've done a great detailed discussion on how to estimate VAR. So, but this is common. Sigma is common. Volatility is common. I can give you a similar example about options. In options, what happened? The prices are fixed. Have you heard about Black and Scholes option pricing model? Black and Scholes.
Yes, sir.
Punajit, please hold. Let others also respond. Understood, Great. Thank you very much. But the other 35 odd students, please react. Anyone else? I'm asking GK thing, nothing else. You think that I'm asking financial routine, not just GK.
I suppose, sir, a little bit.
Please make an attempt. Shivardhan had always been, responding. Yeah, please go ahead, Shivardhan.
Sir, I believe it's based on random walk hypothesis. Like it's a tree kind of structure where we can have both the
Not exactly, the right way. It's a model practically. There's a
yes, sir,
formula which is
based on
used, Black and
heat
Scholes,
equation of
which
physics.
is based upon share price, Brownian motion. We believe that the prices, yeah, but what you are saying is not completely wrong, but prices move in Brownian motion. And a long story, but ultimately when we calculate, we find out the Black and Scholes formula. We have got one more binomial option model, binomial option pricing model. That is, both go hand in hand. So you'll find in both what is common is sigma. You with me, Shivardhan?
Yes, sir.
You are with me? You understood what I'm saying?
Yes, sir. It was primarily based on heat equation of physics.
So look at the utility. I've talked about derivative futures option, both sigma. I'm talking about making a portfolio against sigma. So sigma is so, Zubik, everywhere. You'll find that sigma is present everywhere. You can't say that sigma is not present. Now the question is, when you estimate, all the places you will find that you need to have sigma, which is estimated, forecast. Forecast of sigma is something which is very essential. You would like to know what would be the future volatility and what happen if you have got historical price and you are making use of this formula which I have just shown to you, sigma formula, and you square it, you say I've got variance or SD, then you are only expecting history to be repeated in the future, which is not the case in reality. So you have all likelihood that you need to have forecast value of volatility, and that is best estimated with the help of sigma. So it means what we are understanding, forecast value or understanding sigma becomes very important, and we have to go beyond whatever has been discussed so far. I understand you would have discussed sigma at a few occasions. Professor might have taught you in some other courses. You would have definitely been discussed sigma. So we are again going to talk about in this topic sigma, but I will give you one more statement. I'm making bold statement that the model which we are going to learn, I'm going to give you this name. We are going to learn Garch model, and we have variant of Garch model. So that's why we call family of Garch family of models. So Garch family of models. We have got a few famous Garch models. And just not, so family of Garch family of models. So what is happening that there is nothing better than this. When it comes to estimating volatility, there's nothing better than estimating with the help of or measuring capturing the volatility. The Gauge captures the volatility in the best possible way. The world does not have anything better than Gauge, and that's something which is established fact. From Gauge, you estimate sigma, and then you take it to VAR. I'm not saying that sigma is the best estimate of risk. I'm not saying this, but to estimate sigma, the best model is Gauge. This is what I'm trying to. Gauge or Gauge family of models. You are with me? Are you with me?
Yes, sir.
Srivardhana. Anyone else? Most of you won't respond. So when it comes to volatility, we have to depend upon Gauge, and this is what we are going to study. So what we are going to study today is something which is very important. It's not I'm hard selling it. I'm just trying to share with you that there will be many occasions where you will be asked to estimate volatility, understand volatility, look at the volatility. We have some phenomenon known as spillover. Volatility spillover. Volatility spillover. Again, you will find that you need help from Gauge family of models to understand volatility spillover means, as somebody, I think someone was talking about, how the volatility of one market is having the influence on the volatility of another market. So that we call volatility. So I have done good amount of research work in this field. It's my favorite topics. If you want a little bit more, as far as my writing is concerned, you can go through. You just type my name, you will get a lot of papers on volatility written by me. So we'll be learning this thing. Anything from your side? Any question? Show you one paper.
Sir,
Yeah, please
Gauge
go
is
ahead.
like a model, right?
Right, Gauge is like I've shown you one formula on this. No, what is this formula all about? How do you look at this formula? Yeah, this. How do you say? What is this? Yeah, please react. What is this? It's a model. Model to estimate the volatility or SD. So practically everything is a model in a way. Yeah.
Okay, sir. Yes, sir.
One description is nothing but a model. So similarly, Gauge is also a description. I'll show to you. Everything is ready for you.
Yes, sir.
So I just wanted to show you one. I have something. Okay, I'll show you a little later. So let's talk about how it works. I'll show you the. Let's have a look on the model, just because I think somebody said. So look at this. This is one of the ways by which Gauge. So we have got Gauge, Gauge M, Gauge T, E Gauge. I'll give you some at least Gauge and E Gauge. So this is a model. Please pay attention to the model. I'll write the a little easy form so that you can follow it. I'll get back to that complicated structure of Gauge, and I'll show you the E Gauge also. So what happened? I'll show you the Gauge obviously. Sigma sigma T sigma T square is equal to alpha 0 plus alpha. And you remember when we run regression, we get the error term. So this is T minus 1 square plus we have got beta, which is having the lag term of this. This is with T and we'll have T minus 1. Here we go. This is one form of Gauge. And here what we are saying that Gauge is usually written as P and Q. P is the lag term which is present here. Q is lag term present here in this. So I have taken Gauge 1-1 model, which is in vanilla most popular format of estimating volatility. So we have to come to this level. Let me explain to you how it is coming. You remember heteroscedasticity? Some of you must be remembering when we talked about multiple regression, we talked about it is the coefficients of regression model is estimated with the help of optimum least square. And then I said that OLS depends on certain assumptions. A few very strongly articulated assumptions were heteroscedasticity, multicollinearity, and as we talked about time series, I added autocorrelation also. So let's come back to the discussion on heteroscedasticity. Some of you must be remembering at least what is heteroscedasticity.
So variation not being constant across the independent variable.
Right. What we are saying that variance of the error term with respect to the independent or exogenous variable should be constant. That is something which is the assumption. And if this assumption is not holding true, then we won't get appropriate betas. We want appropriate betas, then we have to have, otherwise again I have discussed that OLS is not blue, or it has got the problems that beta estimated is not reaching to the real beta. So that issues will be there. So estimation will not be correct. And sometimes we have got issues that T or F statistics, F for testing the model, T for testing the coefficient, will not give you the valid results. Invalid results are there. So you want that the estimations are done correctly. These tests, hypothesis testing are working normally or in the within the valid domain. Then this, along with other assumption, should hold true. So we have discussed if it is not heteroscedasticity is not there, then or homoscedasticity is not there, the problem of heteroscedasticity is there, then we can estimate the robust estimation can be done, and we tweak with the standard error of estimation, and we manage anyhow, survive anyhow if there is a problem of heteroscedasticity. I've also discussed that you change the specification of the model. If you have better specification, when I say better specification means you should have correct set of independent variables which are having the genuine impact on the dependent variable. If this correct set of independent variables would have been identified by you, then you will find that specifications are done, and the problem of heteroscedasticities usually go away if you would have corrected the specification. Sometimes it is not possible, then we have solutions all type, and one of the solutions is that we go for robust estimation of the coefficients. Right now, we are talking about another type of heteroscedasticity. Still, we are talking about heteroscedasticity. What we are saying, if variance of error term with respect to time, if it is not constant, then we are getting a different type of heteroscedasticity. Please try to find out the analogy between these two. This was with respect to exogenous variable, I'm sorry, and this is with respect to time. If I just elaborate this description, then I can say the square of u, this square of u is representing the variance in the error term, is equal to, if I put constant also, alpha plus, let me put some simple level so that there is no ambiguity, beta 0, beta 1, ut minus 1 square plus b. B is the regular error term, but right now we are talking about error term. So when we have a series of error term, we have to have another notification for writing the error term. So if beta 1 is significant, then we'll say that this is the variance of u with respect to t is not constant. Or if I'll talk in another language, I'll say that the variance in error term is having autocorrelation. I'm using this so that I'm just interested in giving you brief theory and straight away move out of this. So what I have tried to show to you that heteroscedasticity has been understood that variance of error term when we run any regression should be constant with respect to exogenous variables. That's perfectly all right, should be constant. But another form of heteroscedasticity can be there. If it is not, it means there is heteroscedasticity. So if variance of the error term with respect to time is also not constant, that is another type of heteroscedasticity. So this has been elaborated with the help of this. Variance of u is written as u squared t, which is nothing but the variance of u. If it is serially correlated, what would we as finding it? When beta 1 is significant, it means, what does it mean? That ut or the variance at t is related to the previous time period of variance. It means there is a problem of autocorrelation, but not in the error term, but in the variance of the error term. If this type of situation is there, then we'll say that there is a problem of arch effect, or it's a problem of this type of variance of u with respect to t is not constant, which is another type of heteroscedasticity. So if I just open it, it is known as autoregressive, as you are finding it here. This is autoregressive. If you remember, we have discussed when we say autoregressive, I'm just trying to help you with the name nomenclature. Yt is having association with yt minus 1. This is nothing but yt is having the regression equation with its own lag term. So it is autoregression. That's why this autoregression term is coming in this situation, because variance is having the regression with its own lag term. So autoregressive, that nomenclature is coming. And we are talking about this with respect to time. So that's why conditional, because whenever you write u by t, or for that matter x by y, then a value of x with respect to condition to y. So this is again nomenclature. So I'll say conditional, autoregressive, conditional. And just because variance with respect to time is not constant, so we'll use heteroscedasticity term. So that's why this term arch comes. Why I'm giving you this theory, because whenever we have got any time series and we are interested in estimating the volatility with the help of Garch can be estimated. Precondition, if you remember, we have got preconditions everywhere, whether we are running VAR, vector autoregressive model, or anything else. The precondition of running Garch is that there should be arch effect. If this type of heteroscedasticity is not there, then you can't estimate volatility with the help of Garch. So the possibility of estimating risk with the help of Garch is ruled out if Garch effect is not there. So as we move to EViews, we'll start with this discussion how to explore whether the time series for which we are interested in estimating the risk or volatility using Garch have the arch effect or not. Arch, and then what happened? Arch specification. If I try to write arch specification, then arch specification is written something like that. I want you to take the specification from here. Look at this. This is the Garch model I have written. Look at this. The volatility depends upon variance of the error term, but in a lag form, plus previous period's volatility, because this is the variance. So the variance at a particular point of time depends upon its own lagged value and the lagged value of the error term, the square of the error term. So that is the specification of that. When we practically do it, we don't bother. That's not required. But for time being, just because we are learning, so it's good to have basic theory. That's what I'm trying to share with you. So if I just, for timing, remove this, because by the time this lagged term of volatility comes here, it becomes Garch. But if we don't have this and we continue with lag terms of error, square of the error term, this becomes I'll say beta 0 plus beta 1 ut minus 1 square, beta 2 ut minus 2 square, plus beta 3 plus beta 3 u t minus 3 square. So this is nothing. So likewise, and then again you have got a term, error term VT. So what is happening here? There's a problem that how many lags are required. Again, that P becomes a question mark. And there are many, if P is significantly high, you will find that there are many coefficients to estimate. 3 and 4. So it becomes slightly complicated to estimate. That's why one step ahead we went, the researchers went, and they said that let's talk about uh, beta 0 is here. The first term of, they say let's say p is equal to 1 and have one more Gauss term and lagged value of the Gauss term. And we eventually landed up with this whole notation. Here, t minus 1 square. But as a matter of convention, we use different notations because there's a standard way to write it. We should stick to that standard way. But time being, just because I'm explaining, I'll manage with this. T minus 1 square plus error. So let me write it. If I have to write it in the right form, then right form of Gauss specification. So arch, this is arch. This is arch. And when we knock out with the lagged values of error term and use another lagged value of the volatility itself, it becomes Gauss. And G stands for generalized. So if I give the full name of Gauss, as I said, this is autoregressive conditional heteroscedasticity. I'll say conditional autoregressive conditional heteroscedasticity is the full name of Gauss. So if I write it as a final version, and this is the final version. Here we go. T square is equal to, we usually show it with the help of something like omega plus alpha u t minus 1 square plus beta sigma t minus 1 square. So this becomes the Gauss specification. And just because we are having 1, we'll say Gauss method. So this was very long story in the shortest possible way. I have tried to share with you. This is the Gauss specification. Anything which you would like to ask?
So what is the full form for G?
Generalized auto-regressive conditional heteroscedasticity. Generalized.
Yes, sir.
Anyone else?
So can you show the whiteboard again?
Yeah, with you. Dakshit Kumar talking to me one day. Where is he? Is he there? Dakshit Kumar. Dakshit Kumar.
Oh, yes, sir. Yes, sir. I'm here, sir.
Yes, Dakshit. So,
Actually,
with
sir, I
us?
wanted to ask a question on VIX, sir. I was thinking to ask you post this discussion. So I
Sure.
wanted to
Get back to me.
So is it okay, sir, if I can ask you over now?
After the class, offline you ask.
Okay. Okay, sir.
Volatility index we have.
So also in the Gauss P comma Q, P is the number of lag terms and Q is the number of Gauss terms.
If I just give you, this is the P, means P is the lag of error term, square of the error term, rightly said. And this is Q, which is lag of the volatility or the variance term, which we call it, this is known as conditional variance, because square of sigma is variance. So we say conditional. Conditional means whatever information is available regarding the error of this or variance of this. So condition to that. So that's why we call it conditional variance. It is like u square by t. So instead of t, you assume that we are saying that whatever information is available about this, this means suppose this is the error of let's say BSC. So whatever information of BSC is available, condition to that, whatever is there, we call it conditional variance. So Q is the lag term of the conditional variance. Where is Mr. Ayush Roy? Is there? Ayush?
Yes, sir.
Yes, Ayush, you are following me.
Yes, sir.
Right, so we have come to this situation that we have talked about Gaj. I've told you a story of utility of measuring volatility. I shared with you the theory, very basic theory behind Gaj to data, so that we talk about. Yeah, this was also there. You just pay attention to it. This is square of sigma. So this is conditional variance of whatever time series it is representing constant. And this shows that all the lag term, I is 1 to q. I think I've used P and Q in reverse order. That you please, I don't know whether I'm right or they are right, whatever it is. But one is for it's only interchanging of P and Q. So all the lag terms, if lag is more than one, then all to be added. So T minus 1, 2, 3, whatever it is. Similarly, this is the conditional variance term. So whatever is the lag, 1, 2, whatever is there, that all should be added. That's it. So this is the Gauge specification. So let's move to reviews. I'm showing you something which I've been using for the last couple of sessions. The only thing, here, what I've done, I've got BSc. I'll show to you with the help of BSc. And one simple idea that when we talk about volatility, it is always good not to have prices, but prices should be converted into return series. That is always advisable. It serves two purposes. You'll find that the series will become, usually the price series are I1. So when you calculate return, you will find that it becomes, it remains I1, but it becomes stationarity is there. So the stationarity condition of time series is essential whenever you want to model it. So by the time you convert the price into return, you will find that is there. I'll show to you that how it can be. BSc is there. So you just generate series, you write R return BSc. R BSc is equal to you take the log. When I write log in eViews, it is obviously natural log ln, and you write BSc divided by BSc minus 1, and you close the bracket. So what has happened that it has taken something like this. This is the command you have given. What you have said that ln p divided by p minus 1, ln pt then pt minus 1, something like that is coming r at p. So this type of command I have given, and as I generate the series, I have got RBSc here. So if I just show you BSc in your non-likelihood, it should not be stationary in levels. You're finding that unit root test is not rejected. So null of stationarity is rejected. So as I open it and I try again for unit root test in levels only, and you find that null of normalcy has been accepted. So we'll say that null of stationarity is accepted. So we'll say that distribution is null of no stationarity is rejected, and distribution is stationary. Yeah, it is the stationarity is there, and as I go to estimate the Gauge model, what I need to do is I'll go for estimatic question, quick estimatic question. I have the option. I'll click method. I'll move to Arch. And in the specification, I need to just RBSc. I don't want to run right now. I'll show you another because there's a problem because first term would have again created creates trouble in estimating. I'll directly use the series from Excel. So I can close it. I think I have the series with me. Yeah. I'm just using the BSC. I have removed other time series. Here I've got BSC, again, same thing. Only I've just arranged so that first item problem should not be there. So this is, this if you look at, it has come by the same way, ln P2 by P1. And so same thing is there. I've just arranged so that issue of first item is not there when I take it to. So there are 2,703 items, 2,703. So I'll just convert that into preview series. Here you are finding that 2703, so I'll take 279 so that I've got at least a few blank cells so that I can use them for forecast. We can quickly ensure that there is a stationarity there or not in levels. It is rejected, so stationarity is there. No stationarity is rejected. And if I estimate Arch model, again same thing. I'll go for Arch method, and here I'll write RBSC C, and I'll go for one lag time. RBSC, I'll put it -1. So when I put it this way, I'm saying that the auto regression RBSC return series of BSC is regressed with the help of one lag time. And as you find that we had Arch and Gash terms, I said that this is the error term, square of the error term is known as Arch term, and the lagged value of the conditional variance is known as Gash term. For how many minutes I was off? Yes.
So just the last bit. So you're showing on eViews.
I was showing on views. So I'll again estimate the model. Will that be okay if I just re-estimate?
Yes, sir.
So again, go to quick estimate equation.
Your screen is not visible.
Acha, just. It's okay now?
Yes, sir.
This is the view screen, and what we are going for estimating the arch model. Quick estimate equation method. You go for arch, and there R BSC C R BSC with a lag term. And in the options, I'll suggest that go for optimization method, convert that into eViews legacy. Even if you don't do, it will work, but it will take a little more expected estimations within our understanding. So rest are okay, default setting, arch M you take no, none. And we have given one specification, arch term, as I was showing that arch term, this is arch term, this is gauge term. So 1 lakh arch term, 1 lakh gauge term. And that's it. We are going, and here the model is. If you look at here, first of all, these two, both it means alpha and beta. If I'm talking about here, this specification is alpha as well as beta. Alpha is corresponding to the error term. So error, this is the value 0.15, and this is significant. If you look at the value corresponding to gauge term, this is 0.82, which is also significant. So what we are saying that alpha is equal to beta is equal to 0.1530, and p value is coming 0.000, and this is 0.82, 0.823, and p value. Hello? Sir, I'm in a class. Can I come after Abhinav? Hello? Hello? Yeah. So p value is again 000. Yeah. So if you have noticed that here also we are getting the AIC and SIC values. These may be of use when we want to find out that is it okay if we increase the number of lag terms while estimating the gauge model. Right now we have not made any use of estimating the volatility. Rather, what we have done, we have only made some attempt to estimate the conditional volatility. And to do that, we have taken for granted that we are taking P as 1, Q as 1. So here what we are saying that we can have more than one also, we can try. And when we take more than one, what we can do, we can again check if we are having doubt. But as a literature says that always gauge 1.1 is a great model. Gauge 1.1 is supposed to be plain vanilla and gives good results. But it is also possible that you say no, 2.1 is good, or let's say 5.3 is good. So to have such disputes, we need to just write down that what is the AIC value of this, what is the AIC value of this specification, what is the AIC value of 5.3 specifications, and whatever comes. As per the rule, if you remember, this is the error estimation. So in whichever case the error term is least, that can be taken up. So that is the idea. When I say you can still make use of AIC or SIC criteria to decide the best model, but I'll recommend that go for gauge 1.1, which always gives the best. It is not only parsimonious, but it has got other features also. Are you with me?
Yes, sir.
Yes, sir.
We'll calculate alpha, this much is there. So let's talk about alpha and beta. Do you want to forecast first, or shall I discuss about alpha and beta first? What do you want? You want me to tell you the forecast?
Yes, sir. That can do.
Go forecast first, then I'll give you the story behind alpha beta. This has been estimated. Before I give you the idea about this, I have calculated with the help of, look here what I have done. I have straight away calculated the variance of historical values. Historical return series I have got. I have just used the var function. VAR estimates the variance present in the whatever numbers you are giving, variance of that. I could have calculated SDEP also, STDEVP. Same result, I would have squared it, I would have got the same answer. Either way, it will give me the same thing. I have done that. I'll again show you VAR, and here I go. And as you're finding that I'm just form this cell nature, I'm not copying it. So type of the cell I have just changed. So both are same. It's not I have copied. So same thing I have estimated here. And if you look at, these are daily values. So when I've got daily values, so whatever I'll get variance per day. You have to convert variance per day. What should I do? Anyone? If I want to know variance per annum, what should I do?
Into 12.
It's a daily.
Into 365.
365 is again not great number because the market is not functional daily. So close to 250 would be the ideal number. Though it's an approximation, people may say that this and that doesn't matter. This is the trend we follow, and that's why I have done. And here I have got 7.02% using historical. So we'll again go for using the gauge forecasting. One way I did it is coming out to be 4.16, but I'll demonstrate to you. So here we are there. So far we have estimated gauge 1.1. And this is what we have got. I have to forecast. When you look at forecast, then there's an optional element of gauge forecast is there. So you just go for var1. You might have to do it again. So I'm just putting it. I'm giving one more name. So one series will come var1, and this will be 2703 onwards. We have I think 02 we have. Yeah, it's 2702 we have. So we have 0723 onwards. And we don't want any graph as such. We don't want any forecast evaluation. If this happens, I increase one number at 2704. No forecast. R1. Missing values there. Why? What is the missing value? Some first item number might be having some issue. No problem. We have, I don't know. Let me estimate it again. No one. Let's put removed or new. So what we are getting is these are the values we are getting for all the these are all forecasted values. I think one or two might be overlapping, and I think from here onwards, 1 point this is 137 is onwards is the forecast value. We don't have anything historically present. So if suppose we take the last value or any we can take, that depends which period you would like to forecast. Let's say we have taken this, so 1 point, you can copy it and so this is there again. I'll use the same idea which I applied in the historical case, and I'll multiply it by 250, and I'm just calculating giving the same format to the cell. So it is coming out to be slightly different because I have just changed the number of items, so there is a slight change. But point here is you will find that there is a considerable difference between historical volatility and the forecast volatility. Process is clear. You want me to repeat it? The method of calculating the yes, Taner? Shall I do it again?
So just the last part, the forecasting.
Forecasting again. Let it be like that. So forecasting. Let me see what is the 270. So we can start with 2702. So yeah, here is the equation. This is what I have estimated. Option I have just adjusted this. Okay. And forecast. And let's say I'm calling it for right now 11. And here I'm saying 2702. And that's why we were getting the missing value complaints, because the estimation has to start from a point, and that value should definitely be there. So here we have got R11, and yeah, so that depends which period forecast you want to take. As you are finding that as we are changing the value, the forecast values are changing because the point where it is starting, so you'll find slight changes. If I put this, you'll find that volatility forecast will be slightly changing. Yeah. So the point is that there is a still considerable difference between historical value and the forecast value. Within forecast, I'm not saying just whenever we are estimating where we are starting, accordingly, you will find that the estimation value will be having slight changes. But this is the major change which I'm trying to highlight. So whenever you are dealing with volatility, it is always recommended, if you have time and ability, they should definitely go for estimating the Garch based volatility, especially when you are dealing with forecast of the volatility. This is the idea. Yes. I'll complete the discussion on Garch 11. Alpha and beta as you are finding. Alpha is the value of alpha should be close to 0.2 and beta value should be close to 0.8. So closer to 0.8 means more persistent. So this beta value talks about persistence. How much persistent is the estimate. So higher the value of beta, will say that higher the persistence. And similarly, the alpha value should be 0.2, but higher the value of alpha, especially it makes sense when I say higher when we are comparing between two. Higher the value of alpha, alpha signifies the responsiveness. Like there's a news comes in the market and a particular stock market having alpha let's say 0.1530, will be having some response. Let's say there is another time series or another stock prices or stock returns where alpha is 0.17. Then just because alpha value of the second stock prices are more than this, will say that responsiveness towards the news will be higher in the second case. Similar argument can be placed for beta. Right now, this is 0.823. Let's say some other stocks, the beta is 0.89. Then we'll say that persistence means the impact of change will stay longer if the value of beta is high. So beta value is supposed to be, in the range of 0.8 or plus. Higher the value of beta means it is having higher level of persistence. So alpha tells about responsiveness, and beta tells about the persistence. So things are not going to be so clean every time because that depends how many observations you have taken. If you have taken lesser number of observations, you will find that this will not work so nicely. That alpha value might not be less than 0.2, beta might not be more than 0.8. It may give you sometimes negative. So all are variation from the standard observations of GARCH. So we'll say that some or the other issues and model is unable to capture perfectly mostly due to lack of appropriate number of observations. But even if you do not have enough number of observations, alpha beta are not matching the requirement, you can very well use the GARCH specification to at least forecast the volatility. So forecasting part and alpha beta estimation, these are two different things. Alpha beta measures the responsiveness and persistence, whereas if the coefficients are significant, the way we were saying that coefficients are significant, then you can these are the coefficients, alpha beta coefficient significant, then that is good enough to say that a model can be used for forecasting. So forecasting is dependent upon significance of the coefficients. On the other hand, the alpha beta discussion, that depends whether the good number of observations are there and alpha is less than 0.2 and beta is more than 0.8 or not. So that is the brief discussion of alpha and beta. Um, I have still 10 minutes. I hope that if there's any question I can answer, otherwise I'll give you one more idea. So we have estimated beta. Yes, Dikshit, go ahead.
Yes, sir. Alpha and beta, sir, ultimately they are standard errors, right?
No, they are coefficients. They are coefficients.
Oh, sir, they are coefficients.
Yeah. Look at this specification. They are nothing but the coefficients. Coefficient of Arch term and coefficient of Gauss term.
Yeah. But the values computed from the standard error part of the EVUs or not?
The coefficients are not estimated with the help of standard error. The standard error is used for estimating T. So there is a formula again, normal regression specification are there, but the style of estimation will be there different. Like we estimate beta, if you remember regression equation, normal equations are there using OLS, rightly said, optimum least square. But right now, estimation method is not OLS, rather it is maximum likelihood is the method of estimation. You follow me? There is maximum likelihood. So
Okay.
our three popular methods, OLS, maximum likelihood, and GMM, generalized method of moments. So right now, that specification are estimated maximum likelihood. So the value of coefficient which has got chances of coming maximum number of time. So log likelihood function is made. From there, the value of coefficient which has got the probability of coming highest number of time is the selected coefficient. So ultimately, what you are looking at here is the output of optimum this maximum likelihood estimation method. So log likelihood function would have been used, and eventually these are the final numbers which would have been shortlisted, and that has all these things have been done by a computer directly, and you are end up with the final answer.
Okay, sir. I got it, sir.
Oh, I'll show you one more thing. So this discussion is over. I'm just moving to another form of RBSE is something which we have. Let's show me something. One graph. So I'm just having basic plain simple graph. Look at this. So we have got 2702 observations, and what you're finding, these are the movements. So this depicts the volatility. And there are three features which are very specific with the time series. Three features. First feature is, what you are finding as the prices are falling, you will find that they fall in clusters. Clusters, especially here it is more visible, clusters. So when they fall, they go up, they go up. When they fall in bunches. So tendency of financial time series to move in bunches is known as volatility clustering. So I'm talking about three special features of time series, especially financial time series. The first is volatility clustering. Volatility clustering. Second, there are two more things which I want to highlight. Look at the movement. Usually what happened that the movement towards rising and movements towards falling, they are not symmetrical in nature. There is some asymmetry. So that asymmetry is also, though it is not very high, you're finding that falls are high, but here gains are also high. But there is asymmetry when we say that moving up or moving down. So increase and decrease are not perfectly symmetrical. There is some amount of asymmetry. So that is known as asymmetry. Asymmetry, or we also call it leverage effect in financial time series. Third thing I'll show you with the help of one more graph. Something should come, I think. Distribution will give me or something better. I can show you. Yeah, here I can show you. RBSC. Look at here. We are having some histogram and some statistics. Look at, you have studied the statistics by now. What you're finding, the Zark-Bera null of normalcy is accepted. So distribution is normal, no problem. But as you're finding, skewness is close to zero. So you can say it is symmetrical. But look at kurtosis. Kurtosis, the mesokurtic, which is normally distributed, should be close to 3. But you're finding that this is very high. So it is mesokurtic. It's leptokurtic. Leptokurtic because kurtosis, it is the pickedness at the top is very high. So this situation is supposed to be, we call it fat tails. We call this situation, though it is not very clearly visible. So whenever the distribution is not symmetrical or normal, either it is platykurtic or leptokurtic. So in leptokurtic situations, we call it fat tails. So situation of fat tails is also visible. So what happened that these three are the special features which you come across when we talk about financial time series. Volatility clustering, as we have seen in the previous graph. I think here we have, no, it's lost. So volatility clustering, we have seen that movement of either going up or going down happen in bunches. So that is clustering. And then movement of plus and minus are not in symmetrical order. We call it asymmetry. And similarly, we have got tails. The kurtosis is not mesokurtic, which is not symmetrical types. Rather, it is so some type of distribution is having fat tails. So these are the three features which differentiate normal time series from financial time series. So what happened? Whatever we have done so far with the help of Garch model handles this well. Volatility clustering feature of financial time series can easily be captured with the help of Garch family of models, especially Garch models. But what happened when we have got asymmetry, then Garch model are not fit. To capture the leverage effect, we have to have some asymmetrical model. So one of the popular asymmetrical model is exponential Garch, E-Garch. So as we meet next time, most probably on Sunday, we'll talk about how to estimate E-Garch and again the features of E-Garch. And we'll also talk about right now what we have said, only BSC I'm using, like, I mean, this one Y. But suppose I have got more than 1. I've got y1 and y2. So they can also be modeled together, though the specification becomes very difficult. But at least for bivariate model, we can work. So we'll talk about bivariate GARCH, and we'll, as I was talking about spillover effect, we'll study that how the y1 is having its impact on y2 and how y2 is having the effect of y1 in terms of volatility. So what we have done, we have not talked about when we talked about regression, we talked about y beta 0, beta 1, x1 and all those things. So we have seen that how x1 is impacting y. We have also seen the issue of y1, then beta 0 plus beta 1, y2 t minus 1, like that. So there are, and then we have got y2 1t, 2t is equal to another equation where 1t minus 1. So how 1 is getting impacted by the its own lagged values and lagged values of the other endogenous variable, the var setup. So these we have seen, but what we have not seen, how volatility of one series y1 is impacting the volatility of another y series. That can easily be captured with the help of bivariate GARCH. We shall be seeing in the next class. Yes, any questions? So as per my schedule, the schedule Karkar sir had given me, meeting you again on 5th. And this quiz the quiz is over. I'll discuss probably today night. I'll decide when we are going to have next evaluation component. Most probably I'll give you one more assignment based on volatility. So one session on volatility is over. And what we have discussed, what is volatility, how to estimate volatility with the help of GARCH. Within GARCH, I have talked about how to use forecasting using GARCH. And then I have also discussed that using GARCH, you can talk about the tendency of response and tendency of persistence in a time series. So alpha beta very strongly proclaim the tendencies of responsiveness and persistence. So if I just quickly show you, there's a research paper which I thought I'll share with you, published I think a couple of years back. I don't remember exactly. So this paper talks about, I think correctly taken, yeah, this I've used GARCH 1.1, published in 2011, or 9 years back story, and you'll find many things, some empirical evidence of using GARCH 1.1, and so the values, I've used many time series. So the purpose of showing you this, that the GARCH 1.1 is easily used in empirical work to have some conclusion regarding the tendencies of variability, and as you're finding, alpha beta discussions are part of this study. So the GARCH 1.1 is very well related with the empirical estimation research work. There are many more occasions where you'll find that GARCH is used, especially when we are interested in spilling over effect. You'll find that bivariate GARCH also come very handy. Shall I close?
Yes, sir.